At angular velocity and linear speed, two more equations that use the angle or theta here as an angle in radians rather than degrees. Starting off with here, angular velocity is defined as the amount of rotation per unit time. If rotation is measured in radians, then omega, this is a Greek letter omega, represents our angular velocity equals theta over t, where theta is our angular rotation in radians and t is our time that is elapsed. So our angle theta is measured in radians and our t is our time elapsed. As we move forward here, labeling becomes a bigger and bigger part of these problems in the actual formula itself, because we have to have like labels that we can multiply or divide. And just as a quick reminder here, radians, again, is that non-label that we've talked about. So we can multiply or divide any value by radians and keep that same value, or that same measurement. So feet divided by radians is still feet, hours times radians is still hours, and so on. So our time frame, our label does not change if we multiply or divide by radians. Other than that, our labels do have to be the same in order to be able to multiply or divide. One side note here, it will make more sense as we go to our linear speed, but omega, our Greek letter, looks kind of like a W. That is measured in a radians per time, or you might see that measured in revolutions per time. We're going to introduce a second formula that is measured in distance per time, so we just have to be able to differentiate between the two types of values that are presented to us. So radians per time or revolutions per time is our angular velocity. Essentially what we're saying here is angular velocity is measuring how fast something is spinning around in a circle, how fast a tire is moving around, something like that. So here our example to illustrate here. Find the angular velocity in radians per minute of a disk rotating at 33 1/3 RPMs. So RPM stands for revolutions per minute. Our angular velocity then is 33 1/3 revolutions in 1 minute. We want to change this label, essentially is what we're doing here, to radians. Our conversion to change to radians, I'm going to set up a unit conversion here, so we multiply by 1. I want to cancel the label of revolutions, so my revolutions will go opposite here in the denominator. I want to change it to a label of radians, so radians will be my new label here in the numerator. And I want this conversion factor to have a value of 1. So all the way around a circle is 2 pi radians, and that equals 1 revolution. That's a value of 1. It's called a unit conversion. It converts that over to label of radians per minute, and we go ahead and grab our calculator and multiply 33 1/3 times 2 pi. Gets me about 209.4 radians per minute. Okay, so that wasn't really much of a calculation. It was changing a label from revolutions to radians, because that's what we were asked to find here. Typically, that's how we would measure angular velocities in radians per time. Revolutions is kind of a fallback or a shortcut for that. We'll move on here. Linear speed, it measures the speed of a point in a circular motion. V equals r times our angular velocity, or V equals r times omega. You might also see that written as V equals r times theta over t, because if you recall, omega was theta over t, so we've just made that substitution in for omega right here. Either one of those are interchangeable. This might be instances where you have these two given to you separately, so this formula might make more sense. V is the linear speed, r is the radius of our circle, and omega, again, is our angular velocity. So the difference here is our angular velocity was measuring how fast something was spinning. Our linear speed is going to take a point on the edge of that circle and measure its speed at one particular point in time, so how fast it might be flying out that way or something. So a speed at a particular point in time as opposed to how fast it is spinning. Big key here is our linear speed is measured in a distance per time. So backtracking, I wrote down on the previous one, omega, or our angular velocity, was in revolutions or radians per time. Our linear speed is in distance per time. Examples of that might be miles per hour or feet per second, something along those lines. So down here's our first example. I can backtrack one more statement. Labeling becomes, as we've already mentioned, a very important part of this. And it's actually the bulk of the work in these problems more than it is the actual calculations themselves. So now our example. Find the linear speed of a point on the edge of a disk with 10-inch radius if the disk is rotating in 33 1/3 revolutions per minute. Linear speed, we're finding linear speed. V equals our radius is 10 inches. Our angular velocity is 33 1/3 revolutions per minute. So the first thing to note, we have two separate distinct labels here. We have inches and we have revolutions. Those two separate labels cannot be multiplied by each other. So we have to go ahead and convert one of those to a different unit of measure. So we'll change the revolutions over to radians. Same multiplier we had on the last one. One revolution is 2 pi radians. That will cancel out that label of revolutions. Now across my numerator, I'll just put this 1 over 1 for visual effect. I multiply 10 times 33 1/3 and the inches times the radians. Radians is that non-label, so we can multiply those two together and get a label of inches, and we divide by 1 times a minute times 1, or divide by our number of minutes, which gets us 2,094 radian, oops, take that back, not radians, inches per minute. And you can see as a distance per time, which our linear speed is a distance per time. Handful of examples to get us used to solving for these. Find theta in revolutions if omega is 360 radians per minute and our time is 5 seconds. So notice as we set that up, or pick our formula, we're trying to find omega. We're actually trying to find theta, but we're given omega and we are also given t. So that we're going to use this formula because of the variables that are presented here. We have 360 radians per minute equals theta over 5 seconds. So what you'll notice here is we have two different time labels on each side, minutes on this side and seconds on this side. So we have to convert one over the other before we can solve for theta. To do that, my suggestion to you to avoid rounding errors and decimal issues is change this larger unit of measure to a smaller. So on this side, I'm going to set up a unit multiplier and change my minutes. I want to cancel the minutes. I don't want to change it to seconds. So that's how I set up my labels there. That way they will cross cancel here. I want this fraction of a value of 1. I'm assuming we all know 1 minute equals 60 seconds. So by setting it up in that form, my label of minutes will cancel, and I'll have a new label of seconds. So I make my calculations. 360 divided by 60 gives me 6. And my new label is radians per second, and that equals theta divided by 5 seconds. So now we're ready to go ahead and solve for theta. To get theta by itself, we'll multiply both sides by 5 seconds. So we've now isolated theta on this side. 5 seconds have canceled. On the left-hand side, the label of seconds, the numerator and the denominator, so that's canceled. So I now have a product of 30, and I'll go ahead and write the label of radians, again, even though that radians is a non-label, because we have a little bit more work to do. Our problem said to find theta in revolutions. Well, revolutions is not the same thing as radians, so we're going to do another unit multiplier to change this radians to revolutions. I want to cancel the radians. I want to change it to revolutions. 1 revolution equals 2 pi radians. All the way around the circle is 2 pi radians. So you can see here the label of radians has now canceled. Make a calculator note here. I want to divide by 2 pi, so I need to put that in parentheses. So when I divide that, I have 30. Now I'm going to show you how, if I type that in without the parentheses, 2 pi, what my calculator is doing is taking 30 and dividing it by 2 to get 15, then multiplying by 15 by pi to get 47.12. On the flip side, if I take 30 and divide it by 2 pi, I get 4.77, which is my correct answer. So understand your order of operations here with your calculator. Your calculator is extremely literal, but we have 4.77 revolutions when we make our conversion and plug that into our calculator. I'll go a second time here. Find t if omega is 150 radians per second and our theta is 600 radians. Notice the variables presented again. W equals theta over t. We have 150 radians per second here. We have 600 radians here, and we're trying to find our time. Put this in mainly as an algebra situation just so we understand our variable being the denominator. Two-step process here. I'm going to multiply both sides by t. That way on this side I've got rid of my fractions. So I have t times 150 radians per second equals 600 radians. I'm trying to solve for t, so I'll divide both sides by 150 radians per second. On the left-hand side, the reason we divided was because those two will cancel out. I'll be left with t by itself. And then 600 divided by 150 is 4. Radians divided by radians will cancel. 1 divided by seconds, we'll flip the seconds over, and we'll have a time of 4 seconds. Sliding back to the top here, hopefully. One more time with our variables identified. Find r, our radius, if omega is 90 radians per second, our linear speed, or v, is 27,000 centimeters per minute. So you can see here we have our linear speed formula, and we have 27,000 centimeters per minute is our v. We don't know our radius, but we know our angular velocity is 90 radians per second. Noting we see minutes on one side, seconds on the other side, so we'll go ahead and convert this over to the same time frame by my unit multiplier having minutes over seconds, so the minutes will cancel. 60 seconds is 1 minute. From here, the minutes label will cancel. 27,000 divided by 60 is going to give me 450, and that's going to be labeled as centimeters per second. That still equals r times 90 radians per second. I want to solve for r, so I'm going to divide both sides by 90 radians per second. 90 radians per second. So over here I'll write my answer. R is now isolated on this side. 450 divided by 90 is 5. Centimeters divided by radians is centimeters. Seconds divided by seconds cancels out, so our radius is 5 centimeters. A couple more here. This time we're going to have, or these next few, we're going to have to identify our variables rather than have them identified for us. Airplane propeller measures 6 feet in diameter and rotates at 1,800 revolutions per minute. Find the linear speed of a point on the tip of the blade. Find the linear speed. There's our v. 1,800 revolutions per minute. That's an angular velocity situation. And 6 feet in diameter, that will help us find the radius. I'm going to assume or hope we all know the radius is half of the diameter. So v equals r times omega. We have v we're trying to find. If our diameter is 6 feet, our radius is 3 feet, and our angular velocity is 1,800 revolutions per minute. First thing to note is we have a label of feet being multiplied by revolutions. We can't multiply feet by revolutions, so we're going to change those revolutions over to radians by canceling out the label of revolutions and changing to radians. There are 2 pi radians in 1 revolution. That will cancel our label of revolutions. Now, since we're doing unit multipliers all at the same time, I'm just going to keep doing more because it says that we want our answer in feet per second. I already have the feet label here, but instead of seconds, I have minutes. So I'm going to go ahead and set up another unit multiplier to cancel out those minutes. I want to cancel out the minutes, so minutes will go on the opposite from denominator to numerator. I want to change it to seconds, and 1 minute is 60 seconds. Once again, you'll notice my label of minutes canceling. And now when I multiply, I have 3 feet times 1,800 times 2 pi radians. I can take feet times radians, and the label left for my denominator is seconds, so I'll have a label of feet per second when I finish this. 3 times 1,800 times 2 pi divided by 60 is going to get us about 565.5 feet per second. So as you can see there's more labeling that's going on in these problems than there is actual calculations. The calculations themselves are fairly straightforward. Oh, we'll go a couple more here. Find the angular velocity of a stone embedded in the tread of a tire with a radius of 13 inches on a car going 55 miles per hour. Put your answer in revolutions per minute. So we're trying to find angular velocity, which is our omega. Radius is pretty well spelled out here. That's our radius. A distance per time, that is our linear speed. So there's our v. V equals r times omega. We have 55 miles per hour equals 13 inches times our w, or our omega, sorry. I sometimes call it a w because it looks like a w. Notice I have a label of inches on one side and feet on another side, or miles on the other side. So I'm going to change I'm going to leave this off of here for right now. I'm going to take this 55 miles per hour down here, and I'm going to start unit conversions to change those over to inches. One of our unit conversions to change the miles over to feet is knowing there are 5,280 feet in 1 mile. So I've gone down one step. I still want to go down to inches. So my next conversion, I want to cancel the feet and make it inches. And we all know there are 12 inches in 1 foot. So by those two unit multipliers, we've changed our label down from miles to inches. Now, since I'm looking at my directions, I also want to label in minutes. So I'm going to do some more unit conversions and change my hours over to minutes. So I want to cancel my label of hours. I want to change it to minutes. I assume we all know 1 hour is 60 minutes. So we'll cancel those labels out, hours and hours here. And when I make that calculation, that will give me my left-hand side, which is going to be equal to 13 inches times our angular velocity. So I'm going to go ahead and do the 55 times it's 5280 times the 12. 55 times 5280 times 12. I'm going to divide that by 60. So on this side, I have 58,080. That label is inches per minute. That equals 13 inches times my angular velocity. We'll divide by 13. And that divided by 13, I'm running out of space here, so I'm going to move up to the top. My angular velocity is 4,467.69, and the label on that, inches divided by inches, is radians, and nothing divided by the minute, so radians per minute. Notice we also want our answer in revolutions, not in radians, so we have yet another unit conversion to do. 1 revolution is 2 pi radians. That way the label of radians cancels. Oops, not the 2 pi, so let's just cancel the radians, not the 2 pi. And eventually, here to finish this one off, divide, and don't forget to put that 2 pi in parentheses again. We get 711 radians per, 711, I can't write. Let's try that again. 711 radians per minute. Not radians. We converted that. Need to pay attention to myself. Revolutions per minute. Okay, so let's move on here and find our last problem. What is the angular velocity in radians per second of a 26-inch bicycle wheel if the bicycle wheel is traveling at 15 miles per hour? So 15 miles per hour is our linear speed. 26 inches is our diameter, so that will give us our radius. We're trying to find our angular velocity, or omega. So once again, we have V equals R times omega. 15 miles per hour equals, our diameter is 26, so our radius is 13. And you can say with the same situation, we want this in radians per second. I have inches and I have hours, so I have some converting to do. We'll take the 15 miles per hour here and convert it over to inches by putting 5,280 feet in a mile and 12 inches in a foot. Showing those labels cancel, the miles cancel here, the feet cancel here, so I have a new label of inches. We'll go ahead and do a couple more to get our hours over to seconds. So our hour is 60 minutes and a minute is 60 seconds. So here the hours label cancel, here the minutes label cancel. If we make that calculation, we wind up with 264 inches per second equals 13 inches times omega. All I have left, since I have the same time or distance label on both sides, I can divide both sides by 13 inches. The inches label will cancel, and our linear or angular velocity, 264 divided by 13, is about 20.3, and the label on that, because the inches cancel, is radians per second. And there is our look at angular velocity and linear speed.